Hi, in this video we will solve a problem to find the diameter of a shaft which is supposed to transmit a power of 245 kilowatt at 240 RPM. So how to find the diameter is such that the shear stress in the shaft should not exceed a value of 40 Newton per millimeter square. Also, the angle of twist per meter length should not exceed 1 degree. We have to calculate the diameter if the shaft is solid. Also, we have to calculate the diameters of the shaft if it is hollow. Also, it is given that the modulus of rigidity is 80 kilonewton per millimeter square. So before solving the problem, first we have to write down all the values given in the problem. So power P is 245 kilowatts, that is 245 into 10 raised to 3 watts. The speed N is 240 RPM. Also, it is given in the question that the maximum torque may be 1.5 times the mean torque. Sometimes when the shaft starts operating or rotating, the torque values can exceed the operating torque or the mean torque. So in the question, it is said that the maximum torque may reach up to 1.5 times the mean torque. So we have to calculate the maximum torque as 1.5 into T, and we have to use T max in all the equations for calculations. Okay, next it is also given that the maximum shear stress is 40 Newton per millimeter square. So tau max is 40 Newton per millimeter square. The angle of twist is 1 degree per meter length. So theta by L is 1 degree per meter. In radians, that would be 1 pi by 180 radians per meters. So I want to convert all the length units from meters to millimeters. So I'm going to multiply 10 raised to 3 in the denominator to get pi by 180 into 10 raised to 3 radians per millimeter. Also, the value of G is 8 into 10 raised to 3 Newton per millimeter square. Now let's start doing the problem. So here in this sheet, I have given all the equations for calculations for future reference. Okay, let's start the first step. The first step is to find the torque. And we know the equation is 2 pi nt by 60 for calculating the power. We have to calculate the torque from this equation. So T equal to 60 P into 2 divided by 2 pi n. So let us calculate T equal to 60 into 245 into 10 raised to 3 divided by 2 pi into the speed is 240. So this the value would be 9748 Newton meters. But we have to calculate the maximum torque according to this equation, T max equal to 1.5 times the torque. So that would be 9748 into 1.5. That is 14.62 into 10 raised to 3 Newton meters. As I've said previously, I want to convert all the length units to millimeters. So T max equal to 14.62 into 10 raised to 6. I'm going to multiply it by 10 raised to 3 to get the units in Newton millimeters. So the first step is over. We have got the value of the torque. Now we will start calculating the diameter. First we will calculate the diameter of the solid shaft. And we know that the shear stress should not exceed the value of tau max, which is 40 Newton per millimeter square. And the value or the equation to calculate tau max is tau max equal to 16t by pi d cube, where t is the torque and d is the diameter. And as I've said before, we have to use T max in this equation, which we have calculated in the previous step. So if we want to calculate the diameter D from this equation, we know the value of tau max, and we have calculated the value of T max. So we'll rearrange this equation to D cube equal to 16 into T max divided by pi into tau max. So let's calculate the value of D. So D cube equal to 16 into T max we have calculated as 14.62 into 10 raised to 6 divided by pi into tau max is 40. So when you calculate this, the value would be 1.86 into 10 raised to 6. So the value of D would be the cube root of 1.86 into 10 raised to 6. And the value is 123 millimeters. So we have calculated the diameter of the solid shafts such that the shear stress is not going to exceed the value of 40. So the diameter should be at least 123 millimeter or greater than 123 millimeters. But there is also one more constraint or one more condition. That is, the angle of twist should not exceed 1 degree per meter length. So that condition we should satisfy that condition also. How to do that? So we have got the equation for angle of twist, theta equal to TL by Gj, where T is the torque. We have to use T max here in this equation. L is the length, G is the modulus of rigidity, and J is the polar moment of inertia. We have theta by L, so we'll rearrange this equation as theta by L is equal to T by Gj, and T, as I've said, we should use T max in this equation. Now, we know that the value of J is pi d raised to 4 by 32. So from this equation, we have, the value of D, and using this equation, we can solve for D so that the angle of twist doesn't exceed the given value of 1 degree per unit length. So let us do the calculation. So theta by L, we have already calculated in the beginning as pi by 180 into 10 raised to 3. That is equal to T max 14.62 into 10 raised to 6 divided by G is 80 into 10 raised to 3 multiplied by J is pi d raised to 4 by 32. So in this equation, there is only one unknown, which is D. So we can solve for D and find the value of D, which will satisfy this angle of twist condition. So let us do that. So D raised to 4 equal to 14.62 into 10 raised to 6 multiplied by 180 into 10 raised to 3 multiplied by 32 from here will be there. So 32 divided by, in the denominator we have 80 into 10 raised to 3 multiplied by the pi from here will come here. So pi square. So this is the equation. So we can calculate the value as 1.067 into 10 raised to 8. Now we can find D, taking the root. So the value would be 101.6 millimeters. we can round it up to the next highest value as highest integer as 102 millimeters. So we have again calculated another value of d so that the angle of twist condition is satisfied. Okay. Let's see which diameter we have to take for the shaft in the next step. So here, let's now find the final diameter of the solid shaft. So according to two conditions, we have found the diameter from the Tomax condition, that is the shear stress should not exceed 40 Newton per millimeter square. We have calculated the diameter as 123 millimeters, or the diameter should be greater than or equal to 123 millimeters. Also, the second constraint or the criterion says that the angle of twist theta should not exceed 1 degrees per meter length. We have calculated the diameter as equal to 102 mm, or diameter should be greater than or equal to 102 millimeters. The thing is that both the conditions should be satisfied. So if you select this 1 or 2, the first condition we cannot satisfy because 102 is not greater than 123. So the diameter to select is always the largest diameter. So if the shaft should satisfy both constraints, select the diameter with the largest value, which is 123 millimeters. So we have got the solid shaft diameter value as 123 millimeters. So this is the first part of the problem, to find the diameter of the solid shaft. So to summarize, what we have done is we have calculated the diameter according to two conditions, and we have selected the largest value. So this is how you do it. Now we will go to the second part to calculate the diameter of the hollow shaft. So the steps are the same. First, we will use the first criteria, which is the shear stress should not exceed the Tomax value, which is 40 Newton per millimeter square. And in the next step, we will try to satisfy the second criteria, which is the angle of twist criterion. Okay. So for the hollow shafts, we know the equation for Tomax is 16T by pi dO cube into 1 minus K raised to 4. dO is the outer diameter or the external diameter, and di is the inner diameter or the internal diameter. So this K value, so K equal to di by dO. So this is the equation, and in the question it is given that the outer diameter is twice the inner diameter, so this would be 1 by 2. And we have to solve for diameter, so we will rearrange the equation. So dO cube equal to 16T by pi into Tomax into 1 minus K raised to 4. Again, remember that we have to use T max in the place of torque. Now we can substitute all the values as before. This K value is 0.5. All the other values are same as that we have done before. So the value finally we'll get is 1.986 into 10 raised to 6. And we have to take the cube root to find dO. So dO is 125.7. So we can round it up to the next integer as 126 millimeters. So once you have the outer diameter value, the inner diameter is half of that, 126 by 2, which is 63 millimeters. That is from this equation. So we have found the diameter according to the Tomax criterion. Next, we will calculate the diameter again using the second criteria, which is the angle of twist criteria. So the angle of twist equation is same as before. we'll rearrange the equation for theta by L. And J value, we know that J for a hollow shaft is pi do raised to 4 by 32 into 1 minus k raised to 4. So that is the only difference from the previous solid shaft procedure. So this value we have to substitute for J. Otherwise, all the other values are same as before. So when you calculate, you'll get DO raised to 4 as 113.8 into 10 raised to 6, and the DO value as 104 millimeters. So now we have calculated the diameter according to two criteria. One is the Tomax criteria, second is the angle of twist criteria. Now which diameter we should take? The idea is the same. So the final diameter of the hollow shaft from Tomax, we have the diameter value as outer diameter value is 126, and from the second criteria theta, we have the diameter value as 104 millimeters. Now to satisfy both these constraints, select the diameter with the largest value, which is 126. So the external diameter of the hollow shaft is 126 millimeters, and the internal diameter is half of that, which is 63 millimeters. So now we have solved the problem fully. First we have done the solid shaft part, we have found the diameter, and for the hollow shaft, the external and the internal diameter values are 126 and 63. Okay, I hope this helped. Thanks.